Welcome to Gradient Daily. Today, we are examining a structural solution to the primary bottleneck in high-resolution 3D asset generation. The research comes from a team at Tencent, detailed in the paper Hunyuan3D 2.0, Scaling Diffusion Models for High-Resolution Textured 3D Assets Generation. In game development, virtual reality, and industrial design, creating a single production-ready 3D asset requires manual modeling, UV unwrapping, and texturing. This process reliably takes days per object. Open-source generative models have attempted to automate this, but they consistently struggle to produce geometry that strictly aligns with the input image. Their texture outputs also lack the high-resolution detail found in proprietary closed-source models. Hunyuan3D 2.0 addresses this by strictly decoupling shape generation from texture synthesis, executing both through a scalable flow-based diffusion transformer. Rather than computing every variable at once, the system rapidly constructs a highly accurate structural mesh first, preparing a perfect canvas for texturing. High-fidelity, production-ready 3D assets are no longer gated by proprietary, closed-source industry models. The tension in previous 3D generation models stems from joint generation. When a single network attempts to calculate complex structural geometry and high-frequency surface texture at the exact same time, it is forced to average out the outputs, resulting in low-resolution geometric blobs. The researchers bypass this by adopting a decoupled approach. It operates on the same logic as an automotive manufacturing plant. You cast the heavy steel chassis in one facility and apply delicate precision paintwork in another. This logic yields two foundational models. Hunyuan3D-DIT calculates the structural geometry, and Hunyuan3D-Paint calculates the surface detail. This diagram maps the system architecture. Starting with a 2D condition image, the pixel data first passes into Hunyuan3D-DIT to construct the base 3D geometry. The raw mesh is then handed to Hunyuan3D-Paint, where UV mapping and high-resolution textures finalize the asset. This decoupled process strictly enforces condition alignment. The generated 3D geometry is forced to obey the spatial constraints and structural boundaries dictated by the original 2D input image. Separating the geometric casting from the surface detailing bypasses the latent space bottleneck. This division of labor enables the massive computational scaling required for high-resolution generation. Let's isolate the Hunyuan3D-DIT model and examine its underlying architecture. Older shape generation networks relied heavily on UNet architectures, which hit rigid scaling limits when processing dense 3D data. Hunyuan3D utilizes a scalable diffusion transformer, or DIT. Crucially, this transformer replaces standard diffusion with flow matching. Standard diffusion blindly navigates dense noise, generating tangled, inefficient paths to the final shape. Flow matching instead plots a directed, optimized, straight trajectory from pure noise directly to the target. The mathematical mechanism driving this optimization is defined by this continuous time derivative equation. The model calculates the exact vector difference between the target 3D data distribution and the initial noise state. Solving this specific equation ensures the generated mesh adheres perfectly to the dimensional bounds of the 2D prompt image, eliminating geometric drift. We can visualize this process as a chaotic cloud of independent variables rapidly snapping together into a cohesive, solid form. Flow matching elevates shape generation from a statistical guessing game into a highly optimized, mathematically directed path. Once the physical shape is solidified, the pipeline shifts to the texturing phase inside Hunyuan3D Paint. The primary difficulty of texture synthesis is projection. The model must accurately map flat 2D image data onto complex, folded 3D manifolds. Traditional shrink wrapping techniques fail here. Forcing a 2D picture over an irregular 3D object results in distorted pixels, stretched colors, and mismatched seams. To eliminate this distortion, Hunyuan3D Paint is guided by geometric priors. Think of it like a topographical map. The model analyzes the underlying mesh terrain before applying color. It reads the geometry to place edge highlights where light naturally catches, while accurately dropping ambient occlusion shadows down into deep crevices. By forcing the texture network to read the underlying terrain, Hunyuan3D Paint ensures that high-frequency surface details never map to the wrong spatial coordinates. Teaching a model these complex spatial projection rules requires a massive scale of curated training data. This pie chart illustrates the training dataset composition, showing a deliberate mixture of structured 3D mesh libraries, synthetic renderings, and multi-view image pairs. Training on dense point clouds paired directly with multi-view condition images provides the network with the exact coordinates needed to learn accurate 3D to 2D projection. To make this trained architecture accessible, the researchers packaged it into a user-facing platform called Hunyuan3D Studio. Through this studio pipeline, users can input image prompts, manipulate the newly generated meshes, and apply animations directly in the browser. The integration of multi-view training and a browser-based studio enables users to generate production-ready assets without specialized modeling experience. We turn to the evaluation phase, testing Hunyuan3D 2.0 against previous top-tier models. This side-by-side comparative grid from the paper highlights the output difference. The older models produce blurry geometry with heavy artifacts, while Hunyuan3D 2.0 produces crisp, detailed textures. Quantitative metrics confirm this visual evidence. Across standardized benchmarks for geometry detail and condition alignment, Hunyuan consistently outperforms both open-source models and leading closed-source alternatives. However, the discussion section of the paper outlines several distinct physical limitations in the current architecture. The model struggles with highly complex topological genera. Specifically, it has difficulty accurately resolving intersecting holes and internal negative space. It also exhibits a physical failure state when attempting to generate extremely thin structures, where the generated geometry breaks down or snaps under rendering constraints. Furthermore, calculating this level of extreme high-resolution inference introduces significant computational overhead, requiring substantial hardware resources to run locally. Even with these topological hurdles, the model sets a new standard for the level of geometric and texture detail available in an open-source framework. The research presents three critical takeaways. First, decoupling shape and texture is the required step for computational scaling. Second, flow-matching transformers consistently outclass UNets for strict condition alignment. Third, Hunyuan3D 2.0 successfully bridges the capability gap between closed-source enterprise power and open-source accessibility. Thank you for watching Gradient Daily. If you found this technical breakdown valuable, leave a thumbs up and subscribe to the channel. Future generative pipelines will likely iterate on this decoupled architecture, establishing it as a primary method for engineering and populating virtual environments.